In this video, I'll show you how to use the Excel spreadsheet to get the energy of the hydrogen molecule in the ground state and in the excited states. First, let's look at the Schrodinger equation. It's H psi equals E psi. Unfortunately, we cannot solve this equation for hydrogen 2 because it contains 2 electrons and 2 nuclei. But still, we can use quantum mechanical postulate 4 to compute the expectation value of the hydrogen 2 molecule given its wave function. So in this lab, we will take a guess of the wave function for the ground state and then for the first 2 lowest excited states. We plug in the wave function here and here, and then we evaluate this h being applied to the wave function. So we evaluate this first, and then we do a multiplication, and then divided by this integral, we will be able to get the expectation value of the total energy of hydrogen 2. So now let's look at this H. H is the Hamiltonian of H2. It is the total energy operator, and therefore we need to include the kinetic energy of electron 1, kinetic energy of electron 2. Electron 1 is attracted by the nucleus A. Electron 1 is attracted by nucleus B. Electron 2 is attracted by nucleus A. Electron 2 is attracted by nucleus B. Alright, so we have 2 electrons. And then these 2 electrons repel each other. This is the repulsion term. How about the 2 nuclei? They also repel each other. This uppercase RAB is the distance between nucleus A and nucleus B. What about the kinetic energy of the hydrogen nuclei? Well, we can compute the kinetic energy of nuclei separately. For example, we can compute the translational energy of H2 in a box, the rotational energy of H2, and also vibrational energy of H2. And then we can add those 3 numbers, again, translation, vibration, and rotation, to this value, and then we will be able to get the total energy of the H2. However, I think this is the more difficult part because at the room temperature, the translation energy of the hydrogen molecule is simply 3/2 kBt on average, rotation energy 3/2 kBt on average. Vibration energy is a little bit tricky, but it's simply the 0-point vibrational energy of H2, and that can be easily computed given the force constant of the H2 molecule. So let's focus on the more difficult part, this part. This part is called the expectation value of the electronic energy. Again, these 2 are the kinetic energy of the electrons. These 4 terms are the attraction terms between the electrons and the 2 nuclei, and this is the repulsion between the 2 electrons. Alright, this part does not really contain any electron, and this part is really easy to compute, but this part is pretty significant, so I included it here. Now, for this lab, you need to use the Excel spreadsheet, follow the steps here. We will place the 2 hydrogen nuclei at positions so that they are just 1.5 atomic unit away from each other. Again, this 1.5 is the atomic unit, and also in this H, I was using atomic units throughout the entire expression here. Right? Again, this is atomic unit. And given this, we already know the repulsion between the 2 nuclei. It's just 1/1.5. It's 0.6667 atomic unit. That's the repulsion between the 2 nuclei. So this part is a constant. Again, this is the easy part. All right, and then we put this hydrogen 2 in a box. What kind of box? It's going to be a 6 by 6 by 7.5 box. The reason this dimension is 7.5 is because we want to put this hydrogen 2 molecule in that direction. Right? And then what we do is we will somehow randomly sample the positions of the 2 electrons. We will use this random equation equals ren. Okay, this is the embedded in Excel. This will generate a number between 0 and 1. So this ren function minus 0.5 will generate a number between negative 0.5 and positive 0.5. So, right? And then what you need to do, you need to multiply this by the x dimension of the box. So for example, you need to slightly modify this function. This should be equals 6 times this. And in the z direction, you should do equals 7.5 times this. All right? Maybe I should put it here. E.g. all right, equals 6 times this random function minus 0.5. That's for x. For y, it's the same equation. And for z, this 6 should be changed to 7.5. All right? And once you generate the random coordinates for electron 1 and electron 2, and then it's possible to compute the distance between electron 1 and electron 2, and between electron 1 and nucleus A, nucleus B, and also between electron 2 and nucleus A and nucleus B. All right, using this kind of function. And also, you can compute the distance between the 2 electrons. Again, given the coordinates of electron 1 and electron 2, this is the distance between the 2 electrons. Once you have the distances, you can somehow compute the numerical value of those atomic orbitals. So this is phi 1a, phi 1b, phi 2a, phi 2b. So phi 1a is e to the power of negative r1a. So once you have the numerical value of this r1a, you can compute the numerical value of this phi 1a. All right, so this R1a is going to be a random number, and then you get a random value for this wave function as well. What about the kinetic energy? Kinetic energy, we need to use the kinetic energy operator. Once you apply kinetic energy operator to this wave function, after some derivation, you'll get this format. So I'm not going to prove this here, but if you look at this, you probably realize that for a hydrogen atom, negative 1/2, that's actually the total energy. And this part is actually negative potential energy of the electron in the hydrogen atom. Right? So anyway, we are looking at actually total energy minus the potential energy, and that's kinetic energy. All right? So that's why we have this expression here for the kinetic energy of this wave function. All right? And it's impossible to get a numerical value from this directly, but it's possible to get a numerical value for this guy if we know the distance between electron I and nucleus X. All right, so for example, if we are looking at electron 1 and nucleus A, we just plug in the distance between electron 1 and nucleus A, and that's R1A here, plug it in here, plug it in here, you get a number. And that number is that number corresponds to this kinetic energy operator being applied to the wave function. All right, so you need these columns. Why? This is the just the constructive interference for electron 1, destructive interference for electron 1, constructive interference for electron 2, destructive interference for electron 2. All right. And then we're applying the kinetic energy operator to those bonding and anti-bonding orbitals over here. And then let's talk about the ground state and excited states. S0 is the ground state. S1 and T1 are excited states. So S stands for singlet. T stands for triplet. So S0 means, well, we have both electron paired, and they occupy the sigma bonding orbital. And what if we promote one of the two electrons to the anti-bonding orbital, the sigma star orbital? And then we have 4 different ways of arranging these 2 electrons. All right. Again, we have 2 electrons occupying 2 different orbitals. And then you can have actually alpha, 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 beta, beta, alpha, and beta, beta. All right. So that's the spin of the 2 electrons. And also, we need to ensure that the total wave function for this 3 electronic states of them should be anti-symmetrical. So let's say for the ground state, you have electron 1 in the sigma bonding orbital and electron 2 also in the sigma bonding orbital. So these 2 electrons are paired. And then we have this so-called spatial wave function. This is symmetrical. Therefore, we need to multiply this with an anti-symmetrical spin function. All right. So spin function is going to be alpha 1 beta 2 minus beta 1 alpha 2. Anyway, beta 1 alpha 2. And this is the first excited state with this 2 electron paired. So this is the first triplet excited state with the electrons unpaired. So don't worry too much about the expression here. I just want to say this one is symmetrical, this one is anti-symmetrical. So for this one, you need to multiply this spatial function with a anti-symmetrical spin. And for this one is anti-symmetrical already, so we need to multiply this by a symmetrical spin. But later you will see we don't have to worry about those spins that much, because when we use quantum mechanical postulate 4, the integral of the spin function will appear on top and on bottom, so they cancel. All right, so again, sigma is the bonding orbital, sigma star is the anti-bonding orbital. So you have bonding orbital here, anti-bonding orbital here. Okay. Unfortunately, this star in this case is denotes anti-bonding, but in quantum mechanical postulate 4, this star means complex conjugate. So 2 different meanings denoted by the same symbol. So over here, this is just anti-bonding orbital. You're looking at destructive interference here. All right, and we have 3 new columns. Here, rho is electron density, and rho is simply the complex conjugate of psi. But in this case, we're going to use a real function here. So don't worry about complex conjugate. I mean, just the squared modulus of psi is simply this real function psi squared. And then we are also compute, the integral of the attraction terms. It's going to be simple. It's going to be psi star, the complex conjugate of psi times the attraction terms times psi. And fortunately, this is a simple product of 3 terms, psi star, and then the sum of the 4 attraction terms, and then psi. So because it's simple multiplication, so we can rearrange this product so that we combine psi star and psi. So over here, this is the squared modulus of psi. And because psi is a real function, so the squared modulus of psi is simply psi squared. So basically, we just need to evaluate the numerical value of psi squared times the sum of these 4 attraction terms. Why 4 attraction terms? Well, you have 2 electrons and 2 nuclei, then 4 attraction terms. If you have like 20 electrons, 5 nuclei, and then you have 20 times 5, 100 attraction terms. All right, so again, you just use this to compute the attraction integral for the 3 different electronic states. These 3 electronic states have different wave functions. Again, the wave functions are here. All right. Okay, so we're going to compute this repulsion as well in a similar manner. This is the repulsion term. Again, if you have the coordinates for the 2 electrons, you can compute this term, the numerical value of this term, and then multiply by the wave function squared. You get the integral of the repulsion term. Okay, and then don't forget we need to actually get the electron repulsion, we need to do this. Again, on top you have this rho times the repulsion term. On the bottom you have just this rho by itself. And over here I'm not using integrals, I'm using the sum. It's only because the integral is approximately the sum of this terms, discrete values of this term. All right. Kinetic energies are more complicated because we need to apply those operators to psi. So here I'm showing you some derivations. What if we apply the kinetic energy operator of the two electrons to the wave function of the S0 ground state? You get this. And then what if we apply this to the first singlet excited state? It's more complicated, sigma star are bonding and anti-bonding orbitals. And again, sigma is the bonding orbital. We can decompose that to atomic orbitals, so we have two atomic orbitals here. Sigma star is anti-bonding orbital, so we have also two atomic orbitals here, but the sign is negative sign. It's changed. And then if we're talking about just the kinetic energy operator being applied to atomic orbital, it can be expanded here in this manner. And again, this derivation is complex. However, the final result is simple. It's actually the total energy negative 1/2 for the electron in the hydrogen atom minus the attraction term, because the attraction is negative 1 over r, so it's negative 1/2 minus negative 1 over r, therefore it's 1 over r minus 1/2. So really this is the kinetic energy of the electron in the hydrogen atom. So that's fairly simple, and it does have a physical meaning here. Okay, but it's kinetic energy being applied to the atomic orbital. So it's kinetic energy multiplied by the atomic orbital. So this is the wave function of the atomic orbital. All right, so once you computed this part, again, it's complex because you need to kind of, do this first and then combine two of those to get the kinetic energy operator being applied to molecular orbital. And over here, you do some combinations, and then you get this, right? It's complex. And after you get this, you still need to do one more step. You need to multiply this by psi. Actually, it's supposed to be the, again, complex conjugate of psi if you are using quantum mechanical postulate 4. But again, for simplicity, we're using real functions here. So psi star is psi. The complex conjugate of a real function is itself. Okay, so let's label this column in this way. Again, you need 3 columns for the 3 different electronic states. S0, that's the ground singlet state. This is the first singlet excited state. This is the first triplet excited state. All right. So at this point, I want you to kind of just use the fill down option to fill 40,000 rows of data. Why is that? Because we're doing random sampling. It's called quantum Monte Carlo integration. So I would like you to watch another video on quantum Monte Carlo or Monte Carlo integration. How to integrate a high dimension complex function that contains, for example, 6 variables. All right. And also we need to compute the sum of rho because again the wave functions we use are not normalized. So to divide the sum of this guy by the sum of psi squared, we will be able to get the expectation value of this kinetic energy in the middle. So again, just you can somehow think of this as the probability density times kinetic energy, okay, and then you sum it up and then divide the sum by the sum of the probability density, and then that's it, you get kinetic energy. However, mathematically, you need to apply the operators to side first. Physically, you can think of this as just kinetic energy in the middle. Right? If you have time, I would highly recommend you to read a Journal of Chemical Education paper. It's in the appendix. Read the entire paper, and then you will understand this lab much better. So I was just showing you how to get the expectation value of the kinetic energy, repulsion, attraction, and you put everything together, you will get the electronic energy of the hydrogen molecule. And then you include this 3/2 kBt for the translation of the molecule, 3/2 kBt for the rotation of the molecule. Oh, I'm sorry, it's actually 1 kBt for the rotation of the molecule because it's a linear molecule. I'm sorry about that. At the beginning of the video, I think I said 3/2 kBt. So that's for nonlinear molecules. The rotation energy is on average 3/2 kBt. But hydrogen 2 is a linear molecule, therefore the average rotation energy of a linear molecule is just 1 kBt. Vibration energy is much more complex, but roughly it's just the 0-point vibration energy. This is because at the room temperature, rarely we see hydrogen molecules occupying the excited vibrational state. Alright, so once we get the expectation value of the total energy, repeat the same calculation 25 times. It can be easily done. You just need to do copy-paste 25 times. But be sure you copy-paste the numerical value of a cell, okay? And then you can just get 25 different numbers. Actually, they slightly differ from each other. They are all randomly generated total energy of the hydrogen 2 molecule. And then you take the average, you will be able to get a fairly accurate energy of this H2 molecule. All right, and then what you want to do is you want to write the lab report. I want you to compute the average and the standard deviation of 25 sets of results. I want you to plot the atomic orbitals, the molecular orbitals. There are two examples on the first few pages. I want to show you maybe the second page. Over here, that's just the total energy here, the potential energy, kinetic energy, electron repulsion, and attraction for the ground state and the first two excited states. Ground state, the first two excited states, etc. And I want to show you the molecular orbitals here. I think this is constructive interference. This is the density. Again, since it's squared, so that's the density of the electrons in hydrogen 2 versus the Z1. So Z1 is the coordinate for electron 1. And over here, you see the destructive interference. There's a node here in the middle. So something like that. Those are examples of plotting molecular orbitals. All right. And let's see. Yeah, this will give you a bonding orbital and anti-bonding orbital. All right. What else? Oh, exchange energy. I want you to explain what exchange energy is. And I want to tell you this. The triplet excited state has lower energy than the singlet excited state. So you want to explain this. But I want to tell you one thing just to better understand this. If two electrons have the same spin, so both are alpha electrons, they cannot appear at the same position. All right? So that actually slightly lower the repulsion between the two electrons. Why? Because if you have electrons with opposite spins, let's say you have one alpha and one beta electron, theoretically they can appear at the same position. And if they do appear at the same position, the repulsion is infinity. So in the end, the repulsion between one alpha and one beta electron is greater than the repulsion between two alpha electrons. All right? So that's the essence of the exchange energy. But I want you to explain what exchange energy is in your own word. And I want you to state the approximations and assumptions in the spreadsheet calculations. There are a lot of them. For example, we approximate the value of an integral with the sum of maybe 40,000 terms, stuff like that. And I want you to state this quantum mechanical postulate 4 and 6. 4 is regarding the expectation value of a physical observable, and quantum mechanical postulate 6 is regarding the anti-symmetrical nature of the wave function of electrons. All right, so this part is optional, although you can still do this part using webmo.org. It's a website for you to do quantum mechanical calculations using Gaussian or other chemistry software. All right, over here, this is appendix. This is a paper. This is published in the Journal of Chemical Education back in 2014, volume 91, page 853 to page 859. And those are the authors. These two are student authors. Jacob Buchanan got his PhD degree in computational chemistry at the Oregon State University. Benjamin Livingston went to the same university, the Oregon State University. He got a master's degree in mathematics and is now working for, I think, NSA, National Security Association. Anyway, he's now a security guy. He came back to Central to recruit math, physics, and chemistry students for NSA. Anyway, just I encourage you to read this paper and to get a better understanding of the paper. For example, if you look at this, how do we get the expectation value of repulsion? Well, we use postulate 4, so you evaluate this integral. But it's impossible to evaluate these two integrals exactly, so we're using approximations here. We're actually getting the sum. And to do the sum, we use Monte Carlo integration. So we randomly sample, the positions of the two electrons. Therefore, you see this random sampling here. And in this lab, we sample, I think, 40,000 different cases. In each case, the two electrons are placed at random positions. And this is just the squared modulus of psi, and this is the repulsion term. And v squared is just the v is the volume element, the volume for electron 1. V squared is the volume for electron 1 times volume for electron 2, because we're doing actually a sex two-pole integral with respect to x1, y1, z1, x2, y2, z2. So that's why we have v squared here. Fortunately, this v squared and this v squared cancel because they appear on top and bottom. So, and also the number of samples cancel. So in the end, we just have a simplified equation to compute the expectation value for the repulsion. So really what you need to do is this. You sum up this term. How many times in this lab? 40,000 times. All right, so in each of the sample data, you need to create random positions for the two electrons. Once you have the random positions, you will be able to compute the numerical value for their wave functions. And then you will be able to compute the numerical value of the total wave function of the two electrons, okay? And then you plug it in here and square it. So that's this first term. Second term, again, you have two electrons placed at two random positions. You just need to compute the distance between the two random positions. That's R12. And then you compute 1 over R12. That's the repulsion. So this part is the repulsion. This part is probability density. And then you sum it up. And then divide everything, the sum, by the sum of this probability density only. So simply put, you can see, well, it's not accurate, but you can just imagine this part and this part cancel, and then you get this part. So really, this part is the probability. This part is the physical observable we're interested. If I use buying lottery ticket as an example, let's say 90% chance you'll get 0, 10% chance you'll get $100. So basically, it's 90% chance times 0 plus 10%, you get 100. So 10% times 100, and then divided by 90% plus 10%. So something like that. And then in the end, the expectation value is I think 90% times 0 plus 10% times $100. The result is $10. That's your expectation value. All right. Again, if you do this integrals, it's going to be extremely complicated because, again, we're talking about a sextuple integral with respect to 6 variables because you have 3 variables for each electron, x, y, 1y, z1, x2, y2, z2 for these 2 electrons. That's why it's complicated. So again, just by looking at this, reading this paper, you'll see how I constructed the total wave function of the 2 electrons. This is anti-symmetrical. Okay, this is the spatial function, tells you the position of the 2 electrons. This is the spin function, tells you the spin. This is symmetrical, anti-symmetrical. What about the S1? This is the first singlet excited state. Again, this is symmetrical, this is anti-symmetrical. What about T1? This is anti-symmetrical and this is symmetrical. All right, and by looking at this, you realize that both sigma and sigma star are involved. Over here, sigma and sigma star are both involved. This is because one electron is in the sigma orbital, the other is in the sigma star. Okay, but which one is in the sigma? Which one is in the sigma star? We don't know. We don't care because these 2 electrons are indistinguishable. So by looking at this a symmetrical function, both electrons are occupying the sigma and the sigma star simultaneously. Same here, both electrons are occupying sigma and sigma star simultaneously. All right, and actually for the triplet state, there are actually 2 other spin functions. One is alpha 1, alpha 2. The other is beta 1, beta 2. All right, so anyway, this is a paper. I encourage you to at least spend some time to browse the paper, but if you can read the paper more carefully, you will fully understand this lab. All right, so this is the derivation for this expression. I applied the kinetic energy operator to the total wave function of the triplet state. Okay, there are 1, 2, 3, 4 terms, really complicated, and each term is a combination of 2 terms, and each of these 2 atomic terms is a combination of these 2 terms. All right, but in the end, it's just over here. It's just the total energy of the electron in the hydrogen atom, which is -1/2 atomic unit, minus -1/r, which is the potential energy. So it's total energy minus potential energy. What's that? Kinetic energy. All right. So in the end, this is very simple. All right. So, but you need to kind of just compute this first and plug it in here, and then you get the numerical value here. You get numerical value here, and plug in these 2 values into here. Okay. Again, it's you just need to be very careful. Results and discussion. I did this 25 times, and oh, by the way, the reason I use a box with dimension 6 by 6 by 7.5 is here. So I place this hydrogen 2 molecules along the z direction. Okay, so this is z direction, this is x, this is y. So again, this is just a diagram showing that we have 1, 2, 3, 4 attraction, 1 repulsion between the 2 nuclei. Therefore, the repulsion between the 2 nuclei is 1/1.5, and also we have a electron repulsion term 1/r12. But electrons are waves, so this r12 may change. It can be anywhere. So that's why we randomly put these 2 electrons, maybe here and here, or maybe here and here, or here and here. We do that 40,000 times. So I'm showing you those are atomic orbitals centered at nucleus A and nucleus B. Those are molecular orbitals centered at A and B. At the same time, in the middle, there's constructed interference. This is sigma star. It's 0 in the middle. There's a nodal surface in the middle. Again, this is the paper. I computed the energy of the ground state first, and then compare that with some high-level calculations. For example, hydrofoil calculations using this basis set. This is blue line, and this data is from Excel spreadsheet calculation, and you can see the match is pretty good. Finally, I want to show you some other Excel spreadsheet graphs. This is the total energy comparison. Over here, attraction. You have the ground state, singlet excited state, triplet excited state, and I'm comparing our spreadsheet calculation with hydrofoil calculations with a small basis set and a very large basis set. These two are done with Gaussian or games, I forgot. Just one of the two computational chemistry softwares, and and we have electron repulsion, the potential energy, kinetic energy, etc., etc. All right, so let's see. Here there's some statistics. Don't worry too much about this, but I did the calculation with sampling fewer data and more data. If you sample more data, you get more accurate result. The reference is okay. Anyway, at least please browse this paper, and if you have time, read the paper carefully, and you will be able to understand the lab.